Hello everyone, this is Mr. Dubrow from AP Physics C, and I wanted to make a couple videos kind of highlighting some of the topics in electricity and magnetism that typically give students a bit of a challenge. And we're going to start with, from chapter 21, how to find the electric field of an extended charge distribution. So as an example, I'm going to solve number 97, and I believe you have to do number 98 in the 13th edition for your homework. So what we have is a quarter circle of charge, and we know that the total charge contained is simply Q, and what we want to do is find the magnitude of the electric field in the x and y directions at the point P, or the origin in my diagram. So in order to do this, we're going to need to break things up and find out how much electric field is contributed by a very small amount of charge, dq. So the electric field from a point charge is kq over r squared. So we're just going to kind of integrate this for all the chunks. So if I consider a little piece of the ring, it's going to have a charge of dq, and I can also draw what this electric field is going to be doing at the origin, and I believe that we're given that the charge is negative, so that means that if we're looking at the origin, a positive test charge would experience a field or a force towards dq. And so what we need to do is call that dE, and then we're also going to have to calculate dEx and dEy. Okay. So really what we need to do, we're given that this has a radius of a. What we really need to do is find an expression for dq. And we're going to make use of what we're going to call the linear charge density, lambda. And so lambda is the linear charge density, so it's the total charge divided by the total length. And for our purposes, we're dealing with a quarter circle, so the circumference of a circle would be 2 pi r, and we only want a quarter of that. So we're going to end up saying the length that we're concerned with here is going to be basically pi a over 2. I'll just take that 2 and put it up top here, and then my total charge is Q. So this is going to be equal to my charge density. But the neat thing about this is that this density is constant, at least in this problem, so that means that the density for the total length is the same as the density for a small chunk. Or in other words, dq over dl. So what we can say is that dq is equal to lambda dl. And now what we need to do is find an expression for dl. And so what we know is that if we look at a small segment of length L, that L can be approximated, or dl can be approximated by r, in this case a, d theta. So here's our angle theta, and d theta would be a very small sliver of this ring. So now we're ready to start plugging things in. This means that dE, our small chunk of field, is going to be equal to k over a squared times dl, which is going to be a d theta. And so that's our expression for the electric field, but then at this point we're going to want to split this up into dEx and dEy. And if we look at our diagram, we can see that dEx is just going to be dE cosine theta. I'm being a little bit sloppy with the vector signs. We're just looking for magnitude. I hope you'll forgive me. And dEy is going to be dE sine theta. Okay, so now we're almost ready to integrate. We're going to say that dEx, we'll just look at magnitude, is dE, so in other words, k over a times d theta. And that's going to be times cosine theta. But actually there's one more thing we need to plug in. When we plugged in dq was lambda dl. We kind of forgot about the lambda, so we'll pop that in there too. And similarly for dEy, we're going to have dEy is equal to k lambda over a sine theta d theta. Okay, so now at this point it's going to be fairly straightforward. We're just going to have to integrate, and we can see, looking at the original ring, that we're going from 0 to pi over 2 in terms of our angle. So we want to integrate from 0 to pi over 2, and the k lambda over a is a constant, so Ex is actually the integral of dEx, or just simply the integral of cosine theta d theta. And I'll continue with this. And remembering our calculus, that's going to be negative sine of theta, evaluated from 0 to pi over 2. Okay, so for this, it's going to be k lambda over a, and then we're going to have the sine of pi over 2 is going to be 1, and the sine of 0 is going to be 0. So that's going to give us an x electric field of negative k lambda over a. And don't worry too much about that negative sign. Remember that our charge is negative, so when we plug that in, we're going to get a component in the positive direction. But likewise, the electric field in the y direction is going to be k lambda over a times integral from 0 to pi over 2 of sine of theta d theta. It's pretty much the same calculation. It's just that when we evaluate the integral of sine, we're going to end up with negative cosine, evaluated from 0 to pi over 2. And so that's going to give us can just take that negative sign out and write that the cosine of pi over 2 is going to be 0, and the cosine of 0 is going to be 1. Okay, so that's going to give us k lambda over a. And again, we're just looking at magnitude, so let's not worry about the sign too much. So now the last thing that we need to do is plug in for k, because after all, I've been taking a shortcut. That's 1 over 4 pi epsilon naught. But what about for lambda? Well, we go back up to here, and we see that lambda is actually 2q over pi a. So lambda is 2q over pi a, which means that Ex is really 1 over 4 pi epsilon naught times 2q over pi a squared. Similarly, Ey actually is going to have the same magnitude. We kind of expect this sort of symmetry going on, and it's going to be k, or 1 over 4 pi epsilon naught, times lambda, 2k over pi a, and then that's going to be squared also. So our final answer for the magnitude of Ex or Ey we'll just make sure that everyone knows we're talking about magnitude here. And so we're dealing with q over 2 pi squared epsilon naught a squared. And one thing that's interesting about this is that it does have the form where it's proportional to 1 over r squared. So because pi is unitless, we've got an epsilon naught and a charge in kind of the right place, and so this is going to give us a result that makes sense. Okay, so I hope to make several of these videos, and if you have suggestions for topics you'd like to see covered, just shoot me an email and I'll see what I can do. Thanks, and see you next time.